Okay, welcome to our next section of electrochemistry. We are in section 21.3, known as cell potential. We are going to be using those standard reduction potentials to calculate the overall potential of a cell. So if you do not have it out already, go ahead and grab a standard reduction potential table. Whether you've got your book in front of you and can quickly flip back to the appendix that it was in. And you know what, I'm just going to go ahead and double check which appendix that is. Appendix D. You can flip back to Appendix D. That is the standard electrode potential table. You can also grab one of the laminated potential tables from the front of the room. So have that handy before we get started today, because we're going to use that for a few examples here. Okie dokie. So, a few points to make. Voltaic cells essentially convert the free energy to electrical energy. They convert the free energy available to do some work, and they convert that to electrical energy. And of course, we human beings love to use that electrical energy to do work for us. So voltaic cells convert free energy to electrical energy, and this is proportional to the difference in potential. Okay. We simply call this the cell potential. This actually has a few names to it. The cell potential is one of the more common ones. This would be the capital E of the subcell. Also, this is known as voltage. Okay, since E of the cell is measured in voltage, we typically just refer to this as the voltage of the cell. And an even fancier term that you might run into is the electromotive force. This is abbreviated EMF, all lowercase. So either one of those three terms you can see in multiple different resources. I've noticed our book tends to stick with cell potential. But you know, if you do look up other things on the internet, do other searches, other resources, they could refer to the cell potential as any one of these three things: electromotive force, or just the voltage of the cell. Okay, a few other general points to make. The potential, the potential of the cell is, if it is greater than 0, what you have, is a spontaneous reaction. Whenever you calculate the cell potential of a cell, if it's bigger than 0, you know the reaction proceeds that direction. It's spontaneous. Okay. Likewise, if the potential of the cell, what was I saying? If the potential of the cell is less than 0, guess what? That reaction is non-spontaneous. Spontaneous. Okay. So this becomes an interesting point. If you build a cell and the cell will always be built to run in a spontaneous way. But if a reaction is given to you, written in a certain way, and you calculate it for that reaction, and you get a value that's less than 0, guess what? That reaction doesn't take place because it's non-spontaneous. You know what does happen? The reverse of that reaction would spontaneously happen. So always keep that relationship in mind. That if you calculate a voltage potential of a cell and it's less than 0, meaning negative, it's non-spontaneous and the reaction actually runs the other way. It runs backwards. Okay? And last but not least, what if the cell potential is equal to 0? Huh? Anybody? If it's equal to 0, guess what? You are at equilibrium. No new products are being made, no new reactants are getting used up, and the reaction has come to its close. And again, we call that equilibrium. Okay, so keep those three things in mind. Very, very important. Okay, now a few things are standard cell potential, which is abbreviated, oh boy, what is happening? Whoops, nope, not that L back. There we go. If the standard cell potential, which is abbreviated E with our little circle meaning standard conditions, okay, our standard cell potential is the voltage associated hope I spelled that right, associated with a reduction reaction at an electrode at 1 molar. 1 molar for our solutions is a standard condition. So it's 1 molar for solutions and 1 ATM for gases. Those are our standard conditions. I'll also mention, I wasn't going to write it out, but temperature is also 25 degrees Celsius, otherwise known as 298 Kelvin. If you look at the top of your standard reduction potential table, it says right at the top there, standard reduction potentials in aqueous solution at 25 degrees Celsius. So there's the indicator, hey, 298 Kelvin, that's our standard temperature for these conditions. We also have a few other things to realize. The 1 ATM is pretty much a given. I can't think of any other problems that would have a reaction run at a different pressure. I'll see if I can find some examples. Maybe we can tackle those. But we will eventually look at what happens if our molarity changes. So under standard conditions, 1 molar is the go-to molarity. If a problem gives you a different molarity, we have to calculate it in a very different way. Like I said, we'll tackle that eventually with some new equations. But these are standard conditions. That's what we're going to be calculating for today. Okay, speaking of standard, the standard electrode. Standard electrode that all reactions were compared to was, I'm going to leave this on a cliffhanger. Take a look at your standard reduction potential table. See if you can find it. One of those reactions, one of those reductions on your table was considered the standard that everything was compared to. One of them might stand out as having a value that's different than everybody else's. I'll give you a second to look for it, scan for it, scan for it. You think you found it? Maybe. All right, if you found the hydrogen reduction, you found it. And if you notice its value is different, it's because it's 0. Hydrogen, here I'm back to writing, hydrogen is the standard. I'm going to show you guys an image and explain what that means here. I'm actually going to need to flip to another page, so let's kind of move on. I'm going to clear all this out and show you guys an image here. Okay, here's the idea here, guys. hydrogen was arbitrarily chosen as the standard. If you think about it, right, remember back to our original days with redox, you can't have reduction without oxidation. Neither one can exist on their own. They have to exist together. You're looking at a table, a standard reduction potential table for individual elements. Only one half, right? They're all reductions. Well, how do you measure a reduction unless you compare it to an oxidation, unless you compare it to something? So you can't have just one chemical react. That's impossible. So the scientific community decided that hydrogen was going to be the standard. And what that means is simply this: they were going to call the hydrogen value 0. Okay? So then if you hook hydrogen up to another metal, let's say, for example, zinc. Okay? If you hook up the hydrogen electrode here, this, if I hook up this half cell to another half cell of, say, zinc, and hooked up a voltmeter, the voltmeter would read 0.76 volts. So if I define my hydrogen as 0, then the 0.76 volts that I'm measuring must belong to zinc. And that's actually how this table was created. If they call this electrode 0, all they did was keep hooking up different metals to this electrode, and they'd see what they would read on a voltmeter, and they would build this table. But that 0, that standard, was arbitrarily chosen. Okay. Once we knew then these individual values for just the reductions, we could combine any one of these to one another, and sure enough, these values, when added together, resulted in the overall potential of the cell. So a few things to take note from this this picture right here. You'll notice here's our half cell, right? This is just one half of the reaction. Hydrogen's a gas. So gas is pumped into this test tube right here, and running through the center of the test tube is a platinum electrode. That would be your inactive electrode, right? Platinum isn't going to react very well with anything, and hydrogen's a gas. I need to be able to conduct electrons through this gas, and what better way to do it than through a piece of platinum? Your H positive ions are from your HCl, right? HCl in water isn't actually HCl, it's H positive and Cl minus. Again, the Cl minus, your anion, isn't doing anything. It's the H plus we're interested in. So here's our reduction. And this should be the same thing you guys see on your standard reduction table. You have 2 hydrogen plus ions, 2 electrons equal an H2 molecule. And if you're at 1 atm and 1 molar, you're at standard conditions. And again, we defined this value as being 0 volts. This is your standard hydrogen electrode, otherwise known as She. This type of information doesn't come up all that often. This kind of background knowledge of how our standard reduction table was developed. But it does explain why hydrogen is 0. Again, we just call it that. We define it that way. But it's also interesting to kind of see how some of this information is actually created. If this does ever pop up, then of course you guys will have some background knowledge on what's going on when we talk about the standard hydrogen electrode. Okay, more information about standard hydrogen electrodes can be found in our chapter, but that's pretty much all you guys do need to know and need to worry about. Okay, let's move on. Okay, now we need to worry about what do we do with these values in our standard reduction potential table. So we're still under our standard cell potential. Standard cell potential topic. A few things to take note. The sign of your cell potential, of your reduction potential, the sign changes when a reaction, oh boy, that's supposed to say reaction. There we go. Sign of the reduction potential changes when a reaction is reversed. So to put it simply, if you guys take a look at, I'm just going to go ahead and pick, let's say iodine. If you look down the list, about, what was that, the 10th or so one down, maybe like the 11th, 12th one down, iodine, I2. I2 plus 2 electrons goes to 2I minus. You see it has a reduction potential of 0.53 volts. That's the reduction of iodine. If you wanted to know the oxidation of iodine, it would be the exact reverse of that. And you would take the 0.53 volts and you flip the sign. That would have a negative 0.53 volt potential if you wanted to oxidize iodine. So clearly, iodine is most likely to be reduced because that's more positive than the negative value of it being oxidized. Very important. Keep note of that. The other thing that's important, this is where a lot of students can make a mistake. If you need to multiply your reaction by a coefficient, multiplying by a stoichiometric coefficient, here's the trick. Guess what? It does not change the value. Does not change your cell potential. Okay, very important. You guys have been really used to multiplying by a coefficient and then multiplying your value by that coefficient, by that number. We do not do that here with reduction potentials. If you need to multiply by a coefficient, it does not change the value of E. I know it seems very counterintuitive, and it is something that so many students continue to do, but you don't want to do it here. The reason being, and the trick is, potential, the voltage, it's a ratio. It's actually a ratio of energy to charge. Okay, it's how much energy you get per charge. When you multiply by some stoichiometric coefficient, okay, you alter the ratio, you double it, but the ratio doesn't change. It's still the same ratio of energy to charge. You just get more energy, and therefore more charge. So the ratio does not change, and therefore the potential doesn't change. That's kind of what's going on here. So please do not multiply your value, your potential value, by any coefficients. Okay, that leads us to one very lovely, handy equation. Oh, fudge. Oh my god, I did it again. Come on. All right. Your potential of the cell is equal to the standard cell potential of the reduction. Plus the standard potential of the oxidation. So literally just adding them both together. And that's something very simple that most students typically don't make any mistakes on and don't misunderstand. All you have to do is look up what's the cell potential of my reduction, what's the cell potential of my oxidation, and combine them, and you get the overall potential of the cell. Let's take a look at an example of that in action here. So here's our question. What is the standard electromotive force of an electrochemical cell made of a cadmium electrode in a 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution. There we go. That's our question. A few things to take note of. First of all, it's asking us for the standard electromotive force. That's our standard cell potential. Okay, so since it says standard right here, we should, everything should be at standard conditions. But it's always good to kind of double check that. So it says we're going to be using a solid cadmium electrode in a cadmium solution. So this would be an active electrode. We're doing it in a 1 molar solution, so there's our standard condition. You can always ask yourself, hey, what's the nitrate doing? Hint, nothing. Nitrate's not doing anything. So it's always a good thing to double check. This cadmium solution, the charge on cadmium is a positive 2. Our other cell is going to be made of chromium in a chromium solution, so this is an active chromium electrode. 1 molar again, there's our standard condition. And double checking the charge, here's nitrate not doing anything. But here chromium has a positive 3 charge. Okay. Good question to ask ourselves is which of these is going to be oxidized and which one's going to be reduced. It does not tell us or give us any hint of that. We got to figure out, is it cadmium that's getting oxidized or is it chromium? And then obviously the other one should be the one that's getting reduced. So let's go ahead and write an oxidation. I'm sorry, I lied. Let's go ahead and write reduction reactions for both, because that's what we have to look up. So we should be able to take this information and write 2 reduction reactions. We can write cadmium being reduced. That would be cadmium 2 positive plus 2 electrons goes to cadmium solid. Go ahead and look that one up on your standard reduction potential table. If you take a look at that table, go all the way down, somewhere just a little south of the middle, you should be able to find cadmium 2 positive gaining 2 electrons, and that has a cell potential of negative, let's write that down here, reduction potential of negative 0.40 volts. Let's go ahead and look up the other reduction, chromium. So here we have chromium 3 positive plus 3 electrons goes to chromium solid. Again, we reference our reduction potential table, scan, and a little bit further down you should be able to see chromium 3 positive plus 3 electrons. That has a cell potential of negative 0.74 volts. So now that we've looked up both of these, we should be able to determine which one's going to be oxidized, which one is going to be reduced. So it turns out cadmium here is our winner for what's being reduced. And if that's being reduced, then our lovely chromium is what's going to be oxidized. Okay, very important to make sure you know which one is which. Which one's going to be reduced, which one's going to be oxidized. So I'm going to rewrite these reactions in a way that, in the proper way. So right now I'm going to start by going with our oxidation reaction. Oxidation occurs at the anode. So at the anode of our cell, right? I'll label it again here, oxidation. We're going to have chromium solid giving off 3 electrons and turning into chromium 3 positive ions. Then at our cathode, which is our reduction, we're going to have the same reaction we had up above. We're going to have the cadmium 2 positive gaining 2 electrons, and turning into cadmium solid. Now, I would also like to combine these. Let's figure out what our overall reaction is. So, if we were going to combine these reactions, okay, remember how to balance. In order to combine reactions, I have to make sure that my electrons cancel out. And here we notice our electrons do not cancel out. We have 3 electrons up here, 2 electrons down here. They are on opposite sides, as they should be. Oxidation, electron should be on the right, and reduction, electron should always be on the left. So I need to multiply these by a coefficient to make sure that they do cancel out. If you've been paying attention, our coefficient, oh boy, this one will get multiplied by 2, and this will get multiplied by 3. So it turns out when we do combine everything together, we'll have 3 chromiums, 6 electrons. Oh my god, I can't do my math. Sugar. Multiplying this by 2. This is 2 chromiums. Oh, I could have left that 6. 6 electrons and 2 chromium there. Multiply the bottom one by 3. 3 cadmiums, 6 electrons, and 3 cadmiums. Electrons all cancel out, and our overall reaction, I believe I can fit it down here, 2Cr plus 3 cadmium 2 positive ions turns into 2 chromium ions and 3 cadmium solid atoms. Okay, so there's our overall redox reaction. Fantastic. Now I've run out of space, so I'm going to go to a new page here, and let's go ahead and calculate our overall cell potential. Okay, if you recall our previous equation, our standard cell potential, our electromotive force, is equal to the standard of the cathode plus the standard of the anode. Actually, this is equal to the potential of our reduction plus the potential of our oxidation. Okay, so if you'll notice the standard of our reduction that we looked up from before, standard of our reduction was a negative 0.40 volts. That was from our reduction of cadmium. Remember, cadmium had the bigger reduction potential. Now when we add the oxidation, right, the reduction of chromium was a negative 0.74, but since it's being oxidized, we flip the sign. And that becomes a positive 0.74 that gets added to. We multiply each of these by different coefficients, but remember that does not change our value. So all we have to simply do is add them together. And we wind up with a positive potential of 0.34 volts. So this, the way our reaction is written would be spontaneous with a cell potential electromotive force of 0.34 volts. Simple as that. Really, guys, the only thing you really have to be sure of is which sign do you flip, and then don't forget to do it. Add it up, and you're good to go. We can take this information and we can write our cell notation. If we wanted to, we can start with our anode, our oxidation, which would be our chromium solid, divided line with the chromium, that was 3 positive, and our aqueous solution. Split that up double line with our cadmium 2 positive ions, single line, and our cadmium solid. That would be the cell notation for our electrochemical cell. We could then take that information and we can draw our electrochemical cell. I could draw my beaker here, draw my beaker over here. Okay, make my oxidation blue. This would be our solution of chromium 3 positive ions. I didn't really look back at those reactions. I hope I have what's oxidized correct. Yeah, I'm pretty sure I do. Okay. We would have then our chromium electrode. right? So this is Cr. Over on the opposite side, make this red. This will be our cadmium. 2 positive ions floating around. And we also have our cadmium electrode. I would connect wires. Let's actually run it through a voltmeter. The voltmeter would read 0.34 volts. Well, technically, right now, if I hooked it up, it would read 0 because I am missing a major part. And you should all be screaming at me saying, salt bridge. Yes, we need our salt bridge. Our electrolyte, another common term for a salt bridge. Remember, salt is just an ionic compound that dissolves in water, which is an electrolyte, same thing. So let's draw our salt bridge here. There's our salt bridge. In this case, just a tube. What salt should we fill this up with? Again, whenever salt is chosen, must not react with any of the chemicals involved in your cell. So a good default would be to make the anion the same anion that's already floating around in either beaker. If you recall, our solutions were actually cadmium nitrate and chromium nitrate. So it makes sense that we would have a nitrate salt. And what better cation than sodium? So let's make this a sodium nitrate salt in our salt bridge. And there you have it. These are arguably the most important skills with electrochemistry, ladies and gentlemen. Being able to decide, based on what chemicals you're given, which one will be oxidized, which one will be reduced, what's the overall cell potential of your cell, write the cell notation, and draw or label all the parts to your cell in a diagram such as this. A few things we could add. This is our cathode over here. Oh yeah, well, I forgot a few things. This is our anode. Oh, sugar, I forgot to state where the electrons are going. Electrons, another good question. Which way would they be flowing? Electrons, I'm going to make them a color. Let's go with bright. Electrons are going this way. Electrons are always flowing from anode to cathode. So you want to make sure you were able to label those arrows. Okay, I think I got all the parts there. Okay, that finishes up that problem. Now, the rest of the section kind of goes into large detail and uses lots of words to describe what I consider to be somewhat simple things. So a lot of it you really don't have to worry too much about. If you can do this from this section, I'd say you're pretty good. You should then be able to look at any of the examples that are in this section and kind of understand where the numbers are coming from, how they're adding them together, so on and so forth. Okay, that's going to end our cell potential talk. Again, this one probably represents a majority of the types of problems that you guys are going to see. Next up, we'll start messing around with what happens, or other equations that we can use to relate other very important chemical concepts like free energy and equilibrium constants. And then eventually we'll start messing around with changes in concentration. That gets fun too. Okay, till next time.